All right, so just like the other techniques we've seen, there's sort of an initial format that the equation needs to be in. If it happens to be in that format, then we can apply one of the techniques that we've looked at before. So this is, yet again, another, if it happens to be in this form, we can take advantage of that and go forward from that. Okay, so the process is called an exact equation. So let's kind of go through the mechanics as to what the process is, and then we can look at some specific examples. So we have a function in terms of x and y. So z function, which is really just a fancy way of saying f of x, y. So we're looking at multivariable stuff here. Is a function of two variables with continuous first partial derivatives in the region R of the xy plane. Then recall the partial derivative concept. So the differential for z is the partial with respect to x of the first expression and the partial with respect to y of the second expression. Okay, so in the special case where the function f of xy equals a constant, when I take the differential, the reason why c disappears becomes 0 because I'm taking the derivative of a number, and that happens to be 0. So that gives me this statement right here. Okay, we like these things if they equal 0. That makes our job a little bit easier. Okay, so again, that assumes then that we can find this main function that we are starting off or looking at the differential of this, some sort of main thing, which is why we can apply that. So to shorthand this and kind of make this a little bit so we don't have to write all of this notation over and over again, we refer to a differential expression of m and n. So m of xy dx and n xy dy. And we refer to those partial derivatives as exact differentials of the original function. Okay, so that's the start, is we're going to check to see if we are in fact looking at the same partial, and maybe there's an overarching function that sort of describes what we're seeing here, and that's how we're going to end up solving this. Okay, so the process for what we're going to do is we're assuming we have something in this format. We first verify that it in fact is in this format. So step one is to take the partial derivatives of the two equations we're given. So the partial of m with respect to y and the partial of n with respect to x. And if that statement is true, so if the left side equals the right side, then we know there's some main function that describes where we got those partials from. If you recall from multivariable calculus, kind of go back and kind of why is that true? When you took the partial with respect to x of a function and you took the partial with respect to y of the function, you got two different functions most of the time. But when you reversed and then so you did the partial with respect to x first, and then take the partial with respect to y, you should end up with the exact same statement when you took the partial with respect to x and the partial with respect to y. So in case you visually, you're like, what is he talking about again? Okay, so if I found f of x, and then I found f of y, and then I went and I took the second derivative, what we found is that the partial with respect to x and then additionally with respect to y should be equivalent to the partial with respect to y then respect to x. So it's one of those interesting properties from partial derivatives. So if assuming that statement's true, then we know we're dealing with an equation that's in the format that this process will allow us to solve. Okay. So step two. We've now verified that, yay, it does fit the partial derivative definition. So we're going to integrate, and honestly, it doesn't really matter, but we're just to be consistent, we're going to integrate with respect to m, with respect to x, and when I get an answer there, I'm going to have that function with some constant, or not necessarily constant, but with some function with respect to y. And that's where I'm going to have to be creative and do a little bit of solving. So I think I'm just going to jump into an example and kind of refer back to these steps as far as, well, what are we doing first? What are we doing second? Why are we doing this? And hopefully that'll make sense by the time we get done. Okay, so let's take a look at an example and kind of see what we're talking about here. So first off is to first calculate our m function. So that would be m of xy which should be this piece in front of dx. So that's 2xy. And our n function would be the other piece. So n of xy would be this piece in front of dy. So that's x squared minus 1. Okay, so just as a reminder here, that's if we in fact have a grand f function, and I've done the partial, I'm looking at 2xy, and I've done the partial with respect to y, and I'm looking at x squared minus 1. So I want to take the partial derivative, so I want to find f of xy, which is the partial derivative of m with respect to y, and that's 2x. And then I want to do the same thing with respect to x here. So the partial of n with respect to x, which is just 2x. Okay, so what do we see? We see that these two partial derivatives match. So f of xy is equivalent to f of yx. So I now know that there's a singular function f of xy out there. I just don't know quite what it is. Okay, so we're going to go back then to the initial m function. And that equals 2xy. And I want to integrate that with respect to x. And so that would, hold on. So to make sure I'm consistent in my notation here. So if I'm trying to find that f function, and if I integrate the partial with respect to x, that should give me a sense what the function generally looks like. So 2xy dx. Okay, and so I'm going to integrate with respect to x, which is going to give me x squared y plus, and because I did it with, I integrated a partial with respect to x, that means potentially there could be some function with respect to y that I just don't know about. Okay, so I've got a little bit of a snapshot. I know the main function looks something like x squared y plus, and then in theory some function in terms of y. Okay, so then, so we got our f of x, y here. I'm going to recopy this so I can keep going down. Looks something like that. But I know an expression that represents the partial with respect to y, and that'll actually give me an opportunity to solve for this g of y. So if I take the partial, right, that's that f of y, so that's 2xy plus g prime of y. And I have an expression that already represents that. So then that gives me something to solve for to figure out what g of y is. Sorry, I just made a mistake up here. Okay, so the partial with respect to y would just be an x squared statement here. Okay, so how am I going to find, or how do I know what g prime of y is? Well, go back to our partial with respect to y, that n function that we had initially. Those two guys should match each other. So x squared plus g prime of y is equivalent to x squared minus 1. And so that tells me that g prime of y is equal to negative 1. So if I integrate that, let's just integrate negative 1 dy, I get y. So negative y. Okay, so let's put all of these pieces together then. So I have f of xy equals x squared y minus y. And then in implicit form, that would be x squared y minus y equals a constant. So you give me an initial condition, I can continue solving from there.